into and talk about our DSC lab, or our Thermal Storage Energy Lab, which is going to be discussing and talking about today basically PCM materials. Oops, let me go over here. Thermal Energy Storage Lab, we are going to use a technique called DSC, which is differential scanning. Differential scanning calorimetry. In order to kind of do and perform this lab. So we are going to actually basically in this lab, and this lab, the assignment is going to be a poster session. So you're going to create a poster, you're going to stand in front of your poster, you're going to present, you're going to give elevator speeches, you're going to answer questions, all in this kind of Zoom format, so it'll be pretty fun. And what we're going to be investigating are PCM materials, or phase change. So PCM, phase change materials. So materials which are utilized quite extensively to kind of regulate and store thermal energy and release thermal energy to regulate temperatures. So to keep temperatures at a specific temperature, to keep environments at a specific temperature. So in order to kind of investigate these phase change materials and explore some possibilities, we are going to look at the possibility of using stearic and lauric acid as a binary system. So we are going to figure out and determine a phase diagram of basically X stearic from 0% stearic to 1 stearic, and we're going to draw essentially a phase diagram. And we're going to determine invariant points. We're going to figure out what compositions and what properties are basically desirable for phase change materials. We're also going to look at the thermal stability of materials and the extent of supercooling as well in these phase change materials. So, and then the whole point of this poster is that you're going to essentially design a phase change application with this phase diagram and these other thermal properties. So key thermal properties like the melting temperature, the enthalpy of fusion, the thermal stability, this is a quantitative value, thermal stability, and then delta T is the degree of supercooling. So these are going to be the 4 key thermal properties that we want to kind of investigate in this lab. So we've seen lots of examples of thermal energy storage systems. Again, they basically store energy, which can be utilized at a later time, so solar energy. There's lots of different types of TES systems. And actually, here's the board. We're going to go to our, so let's go to our PowerPoint slide. So,
air conditioners consume large amounts of electricity. Air conditioners mean high costs for investment, operation and maintenance, and cause considerable quantities of CO2. Switch off. It's time to switch to Microbalance PCM. Pleasant indoor climate and energy efficiency. Now available with microscopic wax spheres integrated into building materials for ceilings and walls.
These PCMs are actually integrated inside the walls of buildings.
During daytime, indoor heat loads cause room temperatures to rise fast. When a defined room temperature is exceeded, 23 degrees Celsius for example, Microbalance PCM absorbs surplus heat, preventing the room temperature from rising further.
So that's
the secret of Microbalance PCM: tiny acrylic glass spheres filled with paraffin wax. Initially solid, the wax melts at the defined temperature and absorbs considerable quantities of heat during this phase change. A further rise in room temperature is avoided. When the temperature drops, at night or by using air conditioning systems, the wax solidifies and Microbalance PCM releases the previously stored heat. This process functions throughout the entire life cycle of a building, silently and without electric power, operating costs, maintenance or repairs.
This is the key idea, and actually let's stop here for a second. This is the key idea of a PCM. So for example, in that application, you had a wall, and it had lots of little PCM, Microbalance PCM, phase change materials. So this material was designed to melt at 23 degrees C. So during the day, in the afternoon, when the temperature rises, so the sun is shining on here, the temperature starts to rise, and we go above this 23 degrees C. So as the temperature rises, my material in here will become liquid, and it melts. And melting, as we know from our as we know from our first order, second order phase transition, is a first order phase transition. First order phase transition. And melting is an endothermic process. So to melt, we need to absorb energy. So as the temperature increases, in order to kind of maintain, the melting temperature dictates what this PCM is going to kind of maintain the temperature at. So the temperature is maintained at 23 degrees C because as the temperature increases here, it absorbs energy. Now, and then that brings the temperature back down. So it's absorbing that excess energy by melting. Now, if during the night when it gets really, really, really cold, let's say it's like 18 degrees C, we now solidify again. And solidification is an exothermic process. Exothermic process. So the exothermic process releases heat and it will raise the temperature back to this kind of target temperature or this controlled temperature. So the melting temperature is our critical property here. Now, when I say heat is either absorbed or released, what determines that amount of energy? Well, that's the delta H of melting or the delta H of fusion. So you're starting to kind of see and identify which are the key kind of properties here. Now, this material, there's going to be multiple cycles, right? The hot temperature, cold temperatures, there's multiple cycles per day. We're going to integrate into the walls of a building that's going to last for 20, 30 years. So this material needs to kind of be able to kind of go through this heating and cooling process for probably 30 years or millions of heating and cooling cycles. So we need to make sure that we melt and we solidify at essentially the exact same temperature. Otherwise, if there's a lack of thermal stability, i.e. a lack of like the retraceability of these kind of curves that we're going to see in just a second, then that's not a good material for that particular application. So we are going to focus in this lab on phase change materials. So energy storage, retrieval, et cetera, et cetera. We are going to, there's different types of thermal energy storage systems. So sensible, thermochemical, but we are going to focus on latent heat storage in this class. So we are going to look at that storage system. Thermochemical, not so much in sensible heat, but sensible heat is basically storing and retrieving energy basically just by absorbing the heat via the specific heat capacity of the material. So water would be an ideal candidate for sensible heat storage applications. But soil is much worse. Water has the highest specific heat capacity of any material. So sensible heat storage is just, it's changing the temperature of the storage medium. So it's just sitting there in the environment and it's going to absorb, thermal energy, and then you could kind of retrieve that later on. Yeah. Thermochemical storage utilizes kind of chemical reactions, in reversible chemical reactions. So you can kind of see some examples of here. But again, it's a little bit kind of more complicated. Whenever you're dealing with chemical reactions, there's reactants and products and rate constants, et cetera, et cetera, et cetera. So it's not as attractive. One of the really, really attractive ideas for kind of, these thermal energy storage systems, one of the most powerful and one that constantly wins like basically competitions like at MIT called MADMEC are PCM materials or latent heat storage materials. So basically PCMs or phase change materials. So these materials, these PCMs or phase change materials, are ubiquitous now in applications. We're going to see some examples. If you're watching this kind of still laying in bed today, you're probably sleeping on some phase change materials. But what we're using here is we're using the power, the energy that's released or absorbed upon a phase change, going from solid to liquid. So a latent heat or hidden heat, so the heat of fusion of materials. So there's more energy released than during a phase change than when you're just simply going through or absorbing heat based on specific heat capacity of a material. So there's lots of different candidates. Water would be an excellent candidate, but again, water melting and heating at particular temperatures might not be the best for your application. But you can kind of see some of the kind of key parameters we're going to be looking for. TM, latent heat diffusion. And we're always going to be wanting to get these values in kilojoules per kilogram. We're going to have to do a baseline calibration in our particular experiment, but that's what's going to be happening here. So fatty acids, i.e. stearic and lauric acid. So paraffins are like the small waxy polymers. That's what you saw the micronol PCM. Micronol PCM in our little video. Goober salt's another good one, but fatty acids, that's our lauric and stearic acid that we're going to be investigating in this particular lab. So, what do we want? What makes a good PCM material? Well, the first top priority is a TM that basically is in a desired operating temperature range. So the TM, the melting temperature of our material, determines where we can operate. Where can the application function? You know, the whole point of a PCM material is to regulate temperature, to keep temperature at a specific temperature, and that temperature, that operating temperature, is dictated by the melting. So this is our most important property here. Probably the second most important property is high latent heat infusion. So we want a delta HF that's greater than 150 kilojoules per kilogram. That's it. That's kind of one of our key kind of parameters here. We need to make sure that we hit that value. Some other values that would be really important or kind of beneficial: high density, so that you don't have to have again a large container volume. High specific heat. Again, you could also kind of combine this, so you could have basically a PCM, a phase change material, plus sensible heat storage effects. Another very important, inexpensive, obviously. Another very important parameter is supercooling. So oftentimes, we know that ice, for example, ice should melt at 0 degrees C, solidify, same thing. But oftentimes you'll see that, actually we're going to kind of produce plots like this. We're going to measure the heat flow versus temperature. So, and if this is endo and exo, so we're going to heat and melt, and then we're going to solidify, and you're going to see kind of a difference in the melting and the freezing point here. And this is due to kind of kinetic behavior. So here we're heating up at a certain rate and we're cooling at a certain rate. If your heating rate or cooling rate is high, basically we're not allowing our material time enough to kind of rearrange and solidify. So we're keeping it in kind of in that liquidy, state. So depending on the kinetics and the heating rate, if you increase the heating rate, we're going to increase the this distance here is this delta T. So delta T. And that is your degree of supercooling. Your degree of supercooling. So this difference in temperature between the melting and the freezing point is that delta T. And it's just going to be an absolute value here. So we don't want supercooling because we want, that material to be regulated at a very specific TM. So if it's melting and cooling it at different temperatures, it's going to mess up our application. And the last thing is we want good thermal stability. This is a very important parameter. Again, these are just relative rankings. It's really going to depend on your specific application that you identify in this lab. So I want these plots to be able to kind of reproduce over and over, through millions of cycles, right? Especially for like the regulating room temperature application. But if you start to see shifts in peaks, so as I heat up, if these peaks start to shift, then that's an issue. So you kind of see some of these values. Again, PCMs are ubiquitous now, so it's used in almost every type of bed to keep your kind of bed, cool, feeling nice and cool. Shoes, the kind of blue, with the mountains appearing and looking blue, that's a PCM material. There's an amazing application in India where PCMs were utilized to prevent milk from spoiling, which was a huge issue. Again, using it in construction material, even in clothes, again for snowboarders to make sure that your hands stay warm. So PCMs are utilized quite a bit in textiles and lots of different other applications. So key thing, we are going to be essentially investigating these types of PCM materials, lauric and stearic acid, and we're going to kind of figure out what is our delta H, what is our TM, what is our degree of supercooling, delta T, and what is our thermal stability. And that's going to be essentially a qualitative value that we're going to kind of say. So a good thermal stability or poor thermal stability. So we're going to be developing phase diagrams. So we're going to get into that in just a second. Now, we are going to be looking at phase transitions and DSCs. And we're going to be looking at these thermal plots of the heat flow as a function of temperature. Now we know that entropy is the first derivative of Gibbs. And we also know that we can relate entropy to our kind of, I think it's minus dQ, your heat flow. So this is not delta H enthalpy of fusion, this is delta H heat flow. And when we want these units to be heat flow in milliwatts. So we're going to see a plot like this. So we're measuring heat flow here. So heat flow can be related to entropy, and we know that a melting transition is a first order phase transition. So what we're going to see is a discontinuity at that melting temperature. So that melting temperature will tell us, oh, we have a first order phase transition, a discontinuity here, a peak. So that is going to tell us where the melting temperature is. And we could also integrate this peak to figure out what is the enthalpy of fusion here. So that's kind of the key idea of the analysis that we're going to kind of do. Because we know that entropy is related to heat flow and that melting is a first order phase transition, we're going to see that discontinuity. You're going to see that peak in our DSC plots. And in doing so, we're going to be able to kind of build up, and you might see multiple peaks. So we'll kind of look at that, and we're going to build up the phase diagram. So for example, if I see a peak of H, I have a composition like this. So if I have a single peak, I know I'm solid on this side, I'm liquid on this side. A single peak really indicates probably a pure material, congruent melting point, or a eutectic point. But if I see multiple peaks, so let's say I see like something like this. And then if I see 4 peaks, well, at low temperatures, what am I? So on this side, oh, I'm a solid. I'm a liquid here. So I know this is my temperature of my solidus. This is my temperature of my liquidus. And these two are some other type of intermediate temperature. So some unknowns, again, they could be, relate to, a peritectoid or eutectoid or some type of intermediate temperature 1, intermediate temperature 2. So different kind of components here. So we know that this is our solidus line. This is our liquidus line. But this is a simple binary eutectic. Ours might not be. It might be a little bit more complicated. Hint, hint, hint. So this is our lauric acid. This is our stearic acid, which should have a higher melting point. Melting temperature. Well, it should be stearic, right? More carbons in that backbone, more intermolecular interactions, not intra. Intermolecular interactions, more van der Waals. So this will have a higher melting temperature, around like 73. This will have like 44, 42, 43. So those are the materials that we're going to be kind of looking for. So remember, we're looking for high latent heat of fusion. Again, depending on your application, we're going to look for a specific temperature. We don't want, little or no supercooling, application dependent, but also, rate dependent. Good stability, large number of cycles, easy to integrate, low cost, safe, et cetera, et cetera, et cetera. So these are kind of some of the properties, again, that you'll expect to see. So this is a pretty safe bet. Lauric, stearic acid will be a little bit more on this side, and you can see some of the typical properties here. Formulas graph. So DSC. DSC is differential scanning calorimetry. And we are going to kind of measure the differential heat flow between a sample and a reference pan. Hopefully I've got a nice little. So I have a sample pan. So a sample pan and a reference pan. In my reference pan, you see there's nothing in here, no sample. It's just pure aluminum here. But in my sample pan, I have my material. And what's going to happen is I have thermocouples measuring the temperature here. So I am going to increase temperature from 20 to 100 degrees C. And ramp up this temperature, basically if we look at temperature as a function of time, as we ramp up from 20 to 100, then back down, we are going to be keeping these temperatures. We're going to basically ensure that the temperature of this pan and this pan are the same as we ramp up temperature. But there's going to be a different amount of heat that is going to be transferred in order to kind of reach that temperature. So for example, in the reference pan, why do we have a reference pan? So this is an aluminum pan, this is an aluminum pan. So we need to kind of, if we want to just measure the amount of heat absorbed by our material, our polymer, for example, we need to kind of zero out or subtract that, basically the absorption from the aluminum pan. So we need to kind of zero that out. So that's why there's nothing in that reference pan. So there's going to be a differential amount of heat, i.e. differential scanning calorimetry, that is going to be absorbed or required to raise the sample pan temperature to the same temperature as the reference pan. And we're going to measure that difference in this DSC apparatus. So that's the kind of key idea. We're measuring the differential heat flow as a function of temperature. And at some point, again, we're going to go through that transition where we kind of see that melting. So that's the kind of key idea of differential scanning calorimetry. And you can do a lot more. We can measure, for another time in a different class, you can measure the glass transition temperature. So TG is a second order phase transition. So if you look at heat flow versus temperature, that would be kind of basically this change in slope. So second order phase transition. So you can kind of measure lots of different properties. And DSC is a very, very robust technique. So you get very, very, it's very repeatable. It's very robust. So it's very, very, very excellent technique to kind of utilize. So we are going to be generating and measuring kind of different compositions of lauric and stearic acid, and we're going to develop that phase diagram. It's a composition of stearic, for example. So we're going to kind of measure, see where the liquidus lines, where the solidus lines, where we have multiple peaks, and that's what the DSC is going to allow us to do. So as you kind of mentioned before, if I take the integral of this curve, that's going to give me my enthalpy of fusion. This temperature right here is my melting temperature. Again, I can kind of calculate the slope and give me the specific heat capacity, but we're not going to kind of do this in this particular lab. Again, something for another day. Now remember, melting is a endothermic reaction. So oftentimes on a DSC curve, you'll see this kind of endo up or exo up. So if endo is pointing up here, I know that I'm melting. If instead exo was here, I would read and interpret this graph as, oh, we're cooling, because I know that, except for here, that temperature is, going down, but or increasing here. But this would be a cooling curve because I know that's solidification. But since it's saying that endo is up, I know that I'm melting here. That's the melting transition. So that's kind of the key idea, that you want to be able to kind of label endo, exo, melting, endothermic, solidification, exothermic. So when temperatures increase, I absorb energy in my PCM and I melt. When temperature decreases, my material solidifies and it's exothermic, and heat is released, energy is released, thermal energy is released. So that's kind of the key idea for, again, DSC. We're going to use, again, these normal aluminum pans. You could use a microbalance. We're going to use microbalance as well to kind of measure the mass of our sample in the DSC. And then again, you could kind of watch the next video where you actually see me doing the experiment as well. Now, you're going to see some strange units, microvolts, for example, in our raw data plots. So our heat flow is going to be in microvolts. When we integrate microvolts as a function of temperature, when we integrate our peak, you're going to see this kind of weird like microvolt, milligram, second, thing. So these are not the units that we want. We want here milliwatts for our heat flow. When I integrate my peak, I want to get kilojoules per kilogram. So oftentimes you have to calibrate. And one of the calibrations for DSCs is indium. It's a very, very, very well-studied material, and basically I have a calibration curve here for indium, and this calibration curve kind of allows me to look at what indium should be, what is the kind of enthalpy of fusion, what it should be for indium, and then we could kind of calibrate and recalibrate our apparatus. So to convert from these weird microvolts to our good units, milliwatts and kilojoules per kilogram, for our specific DSC apparatus, it's just multiplied by 0.3. So very, very, very nice calibration, simple calibration factor. So in this experiment, we are going to be measuring at heating rate of 10 degrees K per minute. We're going to scan from basically 0, really 20 degrees C to 100 C for our fatty acids. And we are going to, again, build this phase diagram. We are going to, again, identify these kind of key thermal properties that we've, mentioned. TM, our delta HM, our delta T, our thermal stability, et cetera, et cetera, et cetera. And this is kind of a nice figure that kind of encapsulates the entire lab. So as temperature rises, I absorb heat energy and I'm liquid. As temperature falls, I solidify, exothermic, heat release back in the environment, I'm in my solid state. And we want to thank Dr. Geeta Barrera for the development of this lab at MIT. I worked with her. She was my instructor in the same, very similar lab as a student. I got to work with her basically as a PhD student, as a TA, and I'm very proud to kind of now be teaching this class on my own. So that's kind of full circle, just like this figure, where we've got a full circle on our PCMs. So that is essentially all we've got to do, or the basics of this lab. So there's obviously a lot more information in our kind of lab handout, but the slides kind of tell the story. You could kind of look at the materials and methods, but again, I would watch the video now, in terms of how the experiment was actually performed, and then we'll be off and analyzing our data, and I'll see you at the poster session. Thanks.